Swayam Prabha. Digital India. Educated India.
Let me have your attention. Please take a notebook and write. So you see, we are trying to prove this lemma that basically the idea is that if you take an isometry, isometries are connected to linear maps, and the idea is that the only issue with an isometry not being a linear map is that it need not take the origin to the origin. So if you undo that, okay, namely you look at an isometry which takes the origin back to the origin, then it will be a linear map and it will preserve dot products. Okay, and what is more important is that it preserves the dot product, and that is equivalent to it being an isometry and taking the origin back to itself. Okay, and either of these conditions will mean that it is linear. Okay, so I tried to draw some pictures to convince you that if you look at the parallelogram law of addition of vectors and you try to draw pictures for just an isometry which need not take the origin to the origin, you can see that if it took the origin to the origin and it was an isometry, then it will certainly be automatically a linear map. So it's very important that you can connect isometries to linear maps. And why this is important is because linear maps can be manipulated using matrices. Okay, so that is the whole point. So you want to bring in matrix theory, so there's a decent amount of linear algebra that's involved. Okay, so here is the situation. I start with H from Rn to Rn. Okay, there are two equivalent conditions. One is H is an isometry, and H takes the origin to itself. That is, the origin is a fixed point for H. Okay. Then the second one is H preserves dot products. Okay, where the dot product is the standard dot product. Okay, as you would, for example, define it in 3 dimensions. The same kind of dot product can be defined in n dimensions also, right? Now, so let's try to prove this. So the first thing is, you see, so let us make some observations. So some observations are, let us understand what happens if H preserves dot products. Okay, so you see, if H preserves dot products, okay, that is H of V1 dot H of V2 is equal to V1 dot V2 for every V1 V2 in Rn. Okay, then what does it imply? So you see, you set V1 equal to V2 equal to V, you will get HV dot HV is equal to V dot V, but HV dot HV is norm HV squared, so that will be equal to norm V squared, but then this will mean norm HV equal to norm V. So you see, H will preserve norms. Okay, so what will happen is that setting V1 is equal to V2 is equal to V, HV dot HV is going to be V dot V for all V in Rn, and you are going to get norm HV squared is norm V squared. Okay, and this is going to happen for every V in Rn, but then you can take the square root because the norm is positive, and then you will get non-negative, that is, so you will get norm HV is equal to norm V, okay, for all V in Rn. Okay, so if H preserves dot products, then H preserves norms. okay. And if H preserves norms, it is immediate that H will take 0 to 0, okay. Because what will happen is that if you put V equal to 0, you will get norm H0 is equal to norm 0 equal to 0, and if the norm of a vector is 0, then it has to be 0, okay. So this will imply that H of 0 is equal to 0, okay. Since we have norm H0 is equal to norm 0, which is 0, and this implies if the norm of a vector is 0, then the vector is a 0 vector, okay. So so what is happening, if H preserves the dot product, it has to preserve norms, and it has to take 0 to 0, okay. And in this situation, H will become linear, okay. So H will become linear. How do you see that? So you check for linearity. H will become linear, okay. Why is that? That is because you see we want H0 is equal to 0, okay, already proved above. Then you want H of V1 plus V2 is equal to HV1 plus HV2 for every V1 comma V2 in the n-dimensional space. So H should respect addition, then H should respect scalar multiplication. So these are the conditions for a linear transformation, okay. So H of lambda V is equal to lambda times HV for every lambda real scalar and V a vector, okay. So you need these conditions. The first one is already there, right? Because hey, if you started with H preserves dot products, it preserves norms, so it will take 0 to 0, okay. What about the second one? How do you prove this? So you try to prove that this HV1 plus V2 is HV1 plus HV2. That is the same as proving that the difference vector is 0. So you have to show HV1 plus V2 minus HV1 minus HV2 is 0, and that will amount to showing the norm of that is 0. And the trick is always remember that the norm square is the dot product of the vector with itself. That is always the connection, okay. So want H of V1 plus V2 minus HV1 minus HV2 is 0 vector, okay. So calculate the norm of this and show that it is 0, and use the fact that the norm squared is dot product of the vector with itself. So what will happen is that you will get norm, so norm of this want norm of this is equal to 0, and that is the same as saying norm of this squared is 0. You want that, okay. And norm squared is the vector dotted with itself. So I will just have to compute H of V1 plus V2 minus HV1 minus HV2, dot with itself. So you compute the dot product and then write it out. So you'll get this dot it. This vector HV1 plus V2 dot HV1 plus V2 will be just norm HV1 plus V2 squared. So the first term will be norm HV1 plus V2, squared. Okay. Then I'll get two more square terms. HV1 dot HV1 is going to give me norm H of V1 squared. Then HV2 dot HV2 is going to give me a norm of H of V2 squared. Okay. Then I'm going to get the mixed terms. The mixed terms are going to be I'll get a HV1 plus V2 dot, let us say, HV1 from the first term with a minus sign, and then I'll get the same term when I combine minus HV1 in the first term, dot it with HV1 plus V2 in the second term. So I will get a minus 2 HV1 plus V2 dot HV1. Okay. Then similarly, I'll get a minus 2 HV1 plus V2 dot HV2. Okay. and then I will get also a minus 2, I'll get a plus 2 HV1 dot HV2. Okay, that is with minus HV1 in one term dotted with the minus HV2 in the other term. So this is what I'm going to get. And here is the big deal. I assume that H, preserves the dot product. If it preserves the dot product, I just proved that it preserves the norm. Therefore, the norm of HV1 plus V2 whole squared is the same as norm V1 plus V2 whole squared. And similarly, this is norm HV1 squared is norm V1 squared, norm HV2 squared is norm V2 squared. So I'll get norm of V1 plus V2 the whole squared plus norm V1 squared plus norm V2 squared. Okay, that is the first three terms because H preserves the dot product, so it preserves norms. And here, in these terms, use the fact that H preserves the dot product. H of V1 plus V2 dot HV1 is going to be the same as V1 plus V2 dot V1 because H preserves the dot product. So the remaining terms I have to write it as, so minus 2 V1 plus V2 dot V1. Okay, then this term is going to give me minus 2 V1 plus V2 dot V2. Okay, and then the last term will be plus 2 V1 dot V2. Okay, and if you again use the fact that the norm squared is just the dot product of a vector with itself, so you again convert everything to dot product, and then you see everything cancels out and you get 0. So this term is just going to be V1 plus V2 dot V1 plus V2, and the second term will be V1 dot V1. And the third one will be V2 dot V2. Okay, and then here I'm going to get, so you'll get 0. That's all. Okay. So therefore, this is the calculation that you have to do if you want to write it completely analytically. Okay. So therefore, you see H respects addition. HV1 plus V2 is equal to HV1 plus HV2. Okay. Therefore, so H respects addition. The next thing you have to show is H respects scalar multiplication. So next, want to show H of lambda V is lambda HV. This is for every lambda in R and small v in capital V, in Rn. Okay. So again, to show these two vectors are equal, you take the difference and show that is 0. The difference vector is 0. For that, you have to enough to show that the norm is 0. Then you interpret it as norm squared is 0 and write the norm squared as a vector dot itself. So this is the trick that you have to use. So H lambda V minus lambda HV norm squared. You calculate. This is going to be dot of this vector with itself. And I'm going to get norm H lambda V squared. If I take these two terms, if I take these two terms, I'll get plus lambda squared norm HV squared. Okay, then I have the mixed terms. I will get 2 lambda H of lambda V dot H of V. Okay, and again use the fact that H preserves dot product, so it preserves norms. Therefore, this is the same. The first term is the same as norm lambda V squared. Okay, and the second term is lambda squared into, again H preserves norms. Therefore, norm of HV is the same as norm V. So this is norm V squared. Okay, and then here I am going to get the third term, use the fact that H preserves dot products. So it's going to be minus 2 lambda V dot V. So I am using H preserves dot products and norms. Okay, which essentially came from just H preserves dot products. okay, because that implies H preserves norms, okay. So, but then this is of course 0, okay, because this is I will get mod lambda squared norm V squared, and this is mod lambda squared is the same as lambda squared because lambda is a real number, and here I am going to get minus 2. So somewhere, so I think I have missed a lambda out. So there's an extra lambda here. So there is a lambda here. Yeah. So there is an extra lambda here that I have missed out. Right. Okay. So to write it correctly, I should. So let me rewrite this. Please be careful. So I will write it as minus 2 lambda h. V, if we write it, the other one will be h of dot h of lambda, and here it will be minus 2 lambda squared. So let me write one more step. It's going to be minus 2 lambda V dot lambda, and this term is going to be minus 2 lambda squared norm V squared. So it's going to be 0. Okay. So therefore, the moral of the story is H is a linear map. So therefore, what let me just sum up. Therefore, H preserves dot product implies H preserves norms, and which in turn implies that H of 0 equal to 0. Okay, and you will also get that H preserves dot product and H preserves norms if you want both put together. Okay, these two imply that H is linear. Okay, okay. Of course, H preserves dot product is enough. Okay, but in proving H is linear, I also use that H preserves norms. But that also H preserves norms follows from H preserves dot products. Okay, so H is anyway a linear map. Okay, now so what have we proved? You take a map Rn to Rn. If it preserves dot products, it should preserve. It should be linear. It should take 0 to 0. Not only that, it will also be an isometry. H is also an isometry. That is obvious because H is obviously also an isometry because because it preserves norms basically, because you see H norm of H V1 minus H of V2 will be equal to norm of V1 minus V2 for all V1 comma V2 in Rn. This will happen automatically. And why is this true? Again, this is because so in fact I should not so how do you prove this? Again, you want to prove equality of two norms, try to prove equality of squares and then link it to the dot product. The square of the norm is dot product with itself. So you see, if you start with norm of HV1 minus HV2 squared, you will get, this is HV1 minus HV2 dot HV1 minus HV2. Okay, and this is going to be, if I take dot products, I will get norm HV1 squared, then I'll get norm HV2 squared minus 2 HV1 dot HV2. Okay, but you see this is the same as norm V1 squared plus norm V2 squared minus 2 V1 dot V2, and here in the first two I am using the fact that H preserves norms, and the second one I am using the fact that H preserves dot products. But this expression here is actually V1 minus V2 dot V1 minus V2 if you expand it, and that is the same as norm of V1 minus V2 square. Okay, so the proof that if H preserves a dot product, then H is also an isometry, comes from the fact that norm of HV1 minus HV2 is equal to norm of V1 minus V2. So, so let me, for, okay. Thus, so that means we have proved one way. If you start with the if you start with the map which preserves dot products, then it will be an isometry and it will take 0 to 0, and also it will be linear. Okay, that also we have proved. Okay, also in this case, that is H preserves dot products. We have proved H is linear. Okay. Now try to prove the other way. Start with an isometry. If it takes 0 to 0, prove that it will preserve the dot product and it will be linear. So that's the other way around we want to prove. Okay. Conversely, start with an isometry H such that H of 0 equal to 0. Okay. Then we show H preserves the dot product. Okay. It will then follow from the above that H is linear, and it will follow then that H is linear. That's all. That will come automatically. Okay, because we have already proved that whenever H preserves the dot product, it's going to be linear, right? So you just have to start with an isometry H, so that 0 goes to 0, and you have to just show that the dot product is preserved. So what you do is that you compute, so H is an isometry, implies norm of H of V1 minus H of V2 is equal to norm of V1 minus V2, and this holds for all V1 and V2 in Rn. Okay, and see, the moment you have this, also see, if you have this, what you can do is that you can put V1 equal to V and put V2 equal to 0. Okay, and then use the fact that H takes 0 to 0, and you will get immediately that H preserves norms. Okay, put V1 equal to V and V2 is equal to 0. Then what will happen is norm of HV minus H0 is equal to norm of V minus 0, and the right side is of course norm V. Okay, but the left side you use the fact that H0 equal to 0. So use H of 0 is 0. What will happen is you will get norm HV. So let me write that next term also, minus 0. So this implies norm HV is equal to norm V for all V in Rn. So what happens is that if you have an isometry that takes 0 to 0, it preserves norms, implies H preserves norms. Okay. Okay. So you see this cycle of ideas, whether the map preserves norms, whether the map preserves dot products, whether the map takes 0 to 0, whether the map is an isometry. See, all these things are related. That's what I want you to understand. You have to go through all of them, okay, in any argument. Okay, and the thing is, the way to go from the norm to the dot product is to remember the norm square of a vector is the dot product of the vector with itself. Okay, So H preserves norms, and now you see our aim is to show that H preserves the dot product, and now you can easily verify that. So we want to show you know so let me write H preserves the dot product, that is HV1 dot HV2 is equal to V1 dot V2 for all V1 V2 in Rn. You want to show this. So the key is, again, you use the fact that H is an isometry and H preserves norms. So since H is an isometry, okay, H of V1 minus HV2, norm is equal to norm of V1 minus V2. Okay. Now I can square this and then bring in the dot product. Okay. So that I will get HV1 minus HV2 dot with itself is equal to V1 minus V2 dot V1 minus V2. Okay. And just expand this, then you will get, if you expand this, you will get norm HV1 squared plus norm HV2 squared minus 2 HV1 dot HV2 is equal to, on the right side you will get norm V1 squared plus norm V2 squared minus 2 V1 dot V2. Okay. And then we have just now proved that H preserves norms. Therefore, this term will cancel with this term, and this term will cancel with this term. And if you cancel out the minus 2 on both sides, you get HV1 dot HV2 is equal to V1 dot V2. So it preserves the dot product. Okay. So that is a proof of the theorem. So there is for an isometry, taking 0 to 0 is the same as it preserving dot product. Okay. And which means you start with a map which preserves the dot product. It has to be an isometry and it has to take 0 to 0. And in both of these situations which are equivalent, the map will necessarily be linear. Okay. Now here comes a very, very important observation. We started with an isometry with the definition that it preserves distances. Therefore, it happened that it is an injective map. Okay. Because the definition of isometry is norm of HV1 minus HV2 is norm V1 minus V2. Okay. Now, if HV1 equal to HV2, then norm HV1 minus HV2 will become 0. But norm HV1 minus HV2 is norm V1 minus V2. So norm V1 minus V2 will become 0, and that will force V1 equal to V2. Therefore, what this will tell you is that any isometry is always an injective map. But the point is all isometries form a group. That means isometries should have inverses, and the inverses will also be isometries. But for a map to have an inverse, first of all, it should be surjective. Okay. So where does the surjectivity comes from? The surjectivity comes by connecting with linear maps and noticing that the resulting linear map is invertible. Okay. And noticing that the resulting linear map is invertible comes from the Rank-Nullity Theorem in linear algebra. Okay. So let me make these statements. So you see, note if we start with an isometry f from Rn to Rn, okay, then f is injective. Because f v1 is equal to f v2 if and only if f v1 minus f v2 is 0. That is true if and only if norm of f v1 minus f v2 is 0, and that is true if and only if norm of v1 minus v2 is 0. This step is because f is an isometry. Okay, and this is norm v1 minus v2 is 0 holds if and only if v1 equal to v2. A norm of a vector is 0 if and only if the vector itself is 0. Okay, non-zero vector will have non-zero norm. Okay, so if f takes v1 and v2 to the same vector, then v1 and v2 must be the same vector. So it is an injective map. It's not clear that f is surjective. Okay, and the reason why f is surjective is because you can connect it to something, namely a linear map which is surjective. So now we take so I'll write it here. We can't directly see f is surjective. Okay, now now we take you associate to f. See, the important thing about this arbitrary isometry that f0 is not necessarily zero. Remember, that's the problem with the general isometry. Okay, but a general isometry will of course have this property that the isometry condition is norm of f v1 minus f v2 is norm of v1 minus v2. This is always the isometry condition. Okay, mind you, from this condition you cannot directly write norm f. You cannot write norm f0, norm fv is equal to norm v. You cannot reduce this condition norm fv1 minus norm of fv1 minus fv2 is norm v1 minus v2. From that you cannot write norm fv is equal to norm v unless you know f of 0 is 0. Okay, so that is the issue. And how do you undo it? By composing with the translation which takes the image of 0 back to 0. Okay, 0 goes to f of 0. F of 0 is a vector. Now you have to bring f of 0 back to 0. So you have to translate by minus f of 0. So you define g from Rn to Rn by defined by, you undo the effect of 0 not going to 0. So what you do is that you first apply f. Okay, then so g of v is f of v minus f of 0. You do this. Then the point is that g again is an isometry, but g will take now 0 to 0. Since g is an isometry, and that is just an obvious calculation. G of, if you calculate norm of gv1 minus gv2, by this definition you will get norm of fv1 minus f0 minus fv2 minus f0, and you see the point is that this f0 cancels out and you will get norm of fv1 minus fv2, and that is equal to norm of v1 minus v2. Therefore, norm of gv1 minus gv2 is also equal to norm of v1 minus v2, which says g is an isometry. Okay, but the big deal is that g of 0 is 0. Okay, so you have an isometry now which takes 0 to 0. But what we have proved is that if you have an isometry which takes 0 to 0, then it preserves norm, it preserves the dot product, and it is linear. So this implies, so let me write this g correctly. By what we saw above, g preserves norms and the dot product, and g is linear. Okay, Now what I'm going to do is I'm going to recall a little bit of linear algebra, the so-called rank-nullity theorem. Okay, so it's a fact that I'm going to recall, and whether you do a linear algebra course or not, okay, you guys, engineers, I mean not engineers, anybody, any human being should know linear algebra. Okay, so for God's sake, these are very basic things. Please learn them. It's absolutely down to earth stuff, and you need it like See, the problem is that many times uh, matrices are very easy to handle. You know how to multiply matrices, you know how to take inverse of a matrix, determinant, you know also Cramer's rule, with which you can solve equations. Matrices are very, very easy to handle. These are, concrete things. Whereas if you make the idea of a matrix abstract, that's what is going to give rise to a linear map. Okay, a matrix is only one avatar, it is only one representative of a linear map. And usually the when you go from a linear map to a matrix, you have to fix what is called a basis. And normally you work only with the usual n-dimensional space. There are the so-called standard basis vectors, which consists of zeros in all coordinate except one in the ith coordinate. These are called the standard basis. And all matrices can be treated as linear maps with respect to this basis. But if you go to an abstract space, what will happen is you don't have your abstract space is not necessarily Rn, okay, unless you write an isomorphism. And therefore, for an abstract space, you have to use an abstract basis. And when you write a linear map between abstract spaces, you will get a matrix that depends on the basis you have chosen. Okay, so this is what is done in abstract linear algebra. All right, so it's very, very important that some amount of abstract linear algebra should be learned. But at least as far as this course is concerned, I will use very, very minimal amount of linear algebra. And what I need at this point is the so-called rank nullity theorem. So let me state that. So I'll just say recall. Okay, let phi from V to W be a linear transformation or linear map between vector spaces over a field F. Okay, see, for our requirements, both V and W will be just good old n-dimensional real space and with the usual n-dimensional vectors. And you are going to therefore only apply this to a linear map from Rn to Rn. Okay, and the other thing is that the field that we are going to work is the field of real numbers. All right, so for our purposes, so let me say V equal to W is Rn, and the field is just the field of real numbers. All right, so the following so it's a theorem. So what I'm recalling is a theorem. It is a collection of 2 or 3 theorems which are proved in linear algebra. Okay, so the theorem is that there are several equivalent statements. The following are equivalent for F, for the map F. Number 1, this map is, I called it as phi. The following are equivalent for phi. Number 1, phi is a linear isomorphism. Okay, and a linear isomorphism means that it is bijective. Okay, and its inverse exists, and the point is that the inverse will automatically be linear. So the inverse will be linear, and you will have the inverse will be also an isomorphism. Okay, And so let me say the following thing. So let me put an important condition. This is very, very important. I will make sure that, let me put this restriction that V and W are finite dimensional vector spaces. Okay. I do not want to bring in infinite dimensional vector spaces into this situation. Okay. You can also think of infinite dimensional real space, which is hard to, if you want, it is hard to, it is hard to imagine, but you think of it as a growing sequence of Rn's. So you see R1 as x-axis is sitting inside R2. R2 as the xy plane is sitting inside R3. Okay. And if you want R3 as xyz subspace is sitting inside R4. Okay. If you want R4 as xyzt, Minkowski space time. Okay. So you can keep on doing like this. And if you take this increasing sequence and add infinitum, that is your R infinity. Okay. So you can make sense of infinite dimensional vector spaces, but we are not worried about that. So let me put this condition that these vector spaces are finite dimensional. Okay. So there are several conditions for a map to be a linear isomorphism. Phi is a linear isomorphism. Okay. Basically, this is the same as saying phi is bijective and linear. Okay. This is one condition. The second condition is, you see, phi is injective and V and W have the same dimension. And dimension of V over F is equal to dimension of W over F. They have the same dimension. Okay. So we say, so this involves a little bit of abstraction in the sense that how do you decide that the dimension of a space is n? Okay. So the idea is that a dimension of a space must be equal to the maximum number of linearly independent vectors you can get there. So if you take Rn, you can check that the maximum number of linearly independent vectors in Rn will be n. Okay. For example, if you take R1, just one non-zero vector is enough. Every other vector is a scalar multiple of that. If you take R2, two linearly independent vectors are enough because any third vector can be resolved in terms of these two. If you take R3, three linearly independent vectors are enough, and then that will be a maximum, because if you take a fourth one, the fourth one, can be broken down in terms of these three. And so in the same way, you see in Rn, you will have only n as the maximum number of linearly independent vectors. And this happens in a general vector space. What happens, you prove in a course in linear algebra that, a general vector space, if you try to take a set of maximal linearly independent vectors, the cardinality of that set is always the same. You can have different sets of maximal linearly independent vectors, but the big deal is all these sets will have the same cardinality. And that cardinality, that special number, is called the dimension of the vector space. Okay. So a vector space always has a dimension. So for this, you have to show that bases exist. Okay. A maximal linearly independent subset of a vector space is called a basis. You have to prove bases exist for any vector space, and then you have to prove that any two bases have the same cardinality. And then you can define this cardinality as a dimension of a vector space. Okay. So what is happening here is that for phi to be a linear isomorphism, it's enough that phi is injective as a map and the dimensions are the same. Okay. Then here's a third condition. You can have, instead of phi injective, you can have phi surjective and still the dimensions being the same. So phi is surjective and the dimensions of the vector spaces are the same. Okay. You can have, instead of injectivity, you can have surjectivity. But source and target vector spaces should be the same dimension. All right. Okay. And then here is another important condition. If you, this injectivity or surjectivity can also be captured in terms of, the determinant of a matrix of phi written with respect to basis. Okay. And if the dimensions are the same, you will get a square matrix if you fix a basis for V and W. Okay. And a square matrix literally is invertible. When is it invertible? If and only if its determinant is not 0. So you will also get another condition that the determinant of the matrix of phi with respect to any choice of basis for v and w is not 0. Okay, even for one set of choices, if it happens, it's enough. But you should get a square matrix, so the dimensions must be the same. Okay, so let me write this. Dimension of v over f should be equal to dimension of w over f, and the square matrix with entries in the field representing the map phi relative to basis of v and w has non-zero determinant. And which is the same as saying that it is invertible. That is, this matrix is invertible. Okay, and what is going to happen is that if a map is an isomorphism, then the matrix representing that is invertible, and the inverse map is just given by the inverse matrix. Okay, all right. So for example, if you take v and w to be the same space, all right. So these are all equivalent conditions. All right. Now, what I want to say is that how is it important for us? See, we started with f, an isometry. F need not take 0 to 0. So you cooked up this g by undoing the effect of f not going to 0, and g became a isometry which takes 0 to 0, and therefore it becomes linear. But you see, f and g only differ by translation. So you see, f is f being injective, because f is an isometry, and isometry is always injective. What you cannot see is an isometry surjective. F is injective because it's an isometry. G is also injective because G is an isometry. Okay, an isometry is always injective. But now notice, G is now a linear map which is injective. G is an injective linear map from where to where? It's going from Rn to Rn, same dimension. But what does this theorem tell us? Then it has to be an isomorphism. That means it has to be bijective. Therefore, G has an inverse. Okay, and because G has an inverse, F will also have an inverse. Because G is surjective, F will also be surjective. That is the reason why an isometry is bijective and it has an inverse. And then it is automatic that the inverse is also an isometry. Okay, so it's only from this linear algebra that you get, that an isometry is actually a bijective map, and the inverse is therefore an isometry. Once you show that every isometry has an inverse, then you have literally proved that all the isometries under composition form a group. Because the important property of a group is that every element has an inverse. Okay, and what is not clear from the definition of an isometry is that it is going to have an inverse. Surjectivity is not clear, only injectivity is clear. The surjectivity comes because of this connection with linear algebra, and that connection is made by undoing the effect of 0 not going to 0. Okay, so let me write this. So let me say now G from Rn to Rn is a linear isometry. Okay, so G is bijective. So F is bijective. Okay, and this implies that G inverse is defined and is also a linear isometry. Okay, and it also implies that F inverse is also defined. and is again an isometry, and the net effect of all this, is that the set of isometries form a group and the set of linear isometries also form a group. Okay, set of isometries form a group, okay, and set of linear isometries also form a group. Okay. I have to tell you, so the set of isometries form a group and the set of linear isometries also form a group, where the group operation is going to be composition of maps. Okay, where the group operation will be the composition of maps, because composition of maps is associative. Okay, and for a group you need a composition law, a binary law of composition, which is associative. You need an identity element, and for every element you need inverses. And identity isometry is always there, is simply the identity map itself is an isometry. It does nothing. Okay, so it is trivially an isometry. So this is a group. Now the question is, what is that group? What is this group of isometries? So again, this group of all general isometries differ from linear isometries by only translations. Okay, and there are as many translations as there are vectors. Every vector defines a unique translation. So if you remove these translations away, keep them away, and look at only isometries that take 0 to 0, then you are looking at only linear isometries. So you have this group of linear isometries. So the question is, what is that group? And the answer is, it's the orthogonal group. Okay, it is exactly the collections of orthonormal bases in Rn. Okay, and so this brings in the theory of the orthogonal group into the picture. Okay, so that's what we need to see next. And this again will involve trying to write the map of an isometry as a matrix. So we have to bring in the matrices, and especially we need to bring in the orthogonal matrices into the picture. Okay, so that's what we will do next. All right, so I think I will stop here. We will continue the next lecture.